All right, good morning, everyone. Welcome to VSPG. Today we have a presentation from Dr. Huiming Bao, Neoproterozoic, seawater, sulfate, and sulfide. Um, so today Andre is going to go ahead and introduce Huiming for us.
Okay, it's a pleasure to introduce Huiming. Before I start, just a couple things. So we put in schedule for next year until the summer, and I filled out already a number of spots, but still trying to get a full schedule. So if you have any suggestions, feel free to email to Alex and me, or use the form that we have on internet. And next week we have Don Low talking to us. And with this, I introduce Huiming Bao. So Huiming Bao did his undergraduate studies in Peking University in Beijing, China. Then he followed with master degree in Nanjing University, where he studied, sedimentology, stratigraphy, and paleontology. After it, he came for PhD to US, did PhD in Princeton University, where he worked on oxygen isotopes in iron deposits, iron oxides, which is quite complicated. And at that point, he started to use Doug Rumble lab and got introduced to multiple oxygen isotopes. So he followed on with this with postdoc at University of California, San Diego, working with Mark Timmons on all kind of stuff, all focused around measuring multiple oxygen isotopes, like in sulfate precipitates in Atacama Desert, and getting into Precambrian stuff. And when he was for 20 years faculty at Louisiana University, where he developed a lab and used multiple oxygen isotope mostly to study modern processes, and moved into Neoproterozoic, where he worked on cap carbonates and post-glacial events, which he will, I guess, follow today. And recently, or maybe not so recently, a few years ago, he made a full circle back to Nanjing University, where he had International Center for Isotope Effect Research, build a large lab, including orbit traps and other new instruments, and has a large group and working on multiple sulfur and oxygen isotopes, analysis, but as well modeling. So he has a number of people doing various things, including oxygen isotopes and phosphates and iron oxides and so on. So with this, it's a pleasure to introduce Huiming, and I guess he will give us somewhat alternative story from what he was writing and publishing years from now. It's all yours, Huiming.
Thank you, Angie, and thank you, Alex, and thank you everybody for coming along and share a good time talking about the Neoproterozoic world. Well, let me start by just give you a general sense of my philosophy or my general understanding of how the Earth works. Let's see. So Earth has 92 elements, and most elements doesn't have a redox state like silicon and calcium. So pretty much all the drama or redox chemistry specifically run by those five guys or girls, and then you can see among them right now, the oxygen is the one that has get rid of most of the electron, give it to the carbon, right? And then maybe the sulfide. But I think back in the Neoproterozoic, the drama queen is actually should be sulfur. So that's the background of the story. So I got this figure from Hughes. This is today. The ocean sulfate is 10 to the 19th more. But the river input is about 10 to 12. So as you can see, sulfate can have more than 10 million years resident time. And therefore, you also have a evaporite, which is 10 to 11 on deposit on land, which will give you some microbial recycling of the sulfur. And there's a little bit unknown about the hydrothermal system, but normally the active hydrothermal activity will take away sulfate from the seawater. That's today. But what about Neoproterozoic? Well, one thing we're sure is that probably the riverine sulfate doesn't change much. My guess is that the threshold for oxidative weathering for that partial pressure of oxygen already exceed that threshold. So this one doesn't change, but everything else is probably very low. For example, seawater, or therefore the evaporite amount on the land, therefore microbial cycling. But how low exactly? And can we get more detail on it? So I'm going to talk about three stories related to this Neoproterozoic low sulfate world. And all these three are either published or in press. The middle one is in press. So kind of advertisement of my group's work in last few years. The first one, the massive bedded barite deposits. Well, if you look at this is a mineral ore deposits, and those massive bedded sedimentary barite deposits, and they have a clustering in terms of temporal distribution in Earth's history. And they are clustering around the early Paleozoic. And this is the pink one is the barite in the tonnage that you can synthesize from literature. Now, why is that they concentrate on the earlier or the Paleozoic? And equivalently, you will see some of the sulfide deposits, zinc or lead sulfide deposits, not only in the early Paleozoic, but you can go back to the Mesoproterozoic as well. But barite, the sedimentary barite deposits only occur in the Paleozoic. So this is what we think what happened, because the bearing cannot be accumulated if you have lots of sulfate in the ocean. And therefore you have to have a limited sulfate. Too much sulfate, you cannot have a bearing accumulate. But too little, of course, the bearing doesn't have a sulfate to combine with. Even you have a little sulfate combined, you probably will be eat up by the reduced organic matter. So that's why it happens during a time where the ocean or the seawater sulfate have the just right concentration. So you can have this. So we call this a sulfate limited eosinic seawater model for bedded barite deposits. So you have to, those kind of deposits can only occur in a certain time in Earth's history where the sulfate concentration is limited to a level where occasionally they can be totally, entirely used up, become a sulfide. And the sulfide can coexist with barium. Barium can exist only when sulfate is not there. So the paper we published in 2022 by Dr. Han and us, basically it proposes the idea that if you have a massive beta barite, the only way to have that is because it's determined by this long history of the evolution, the redox history of the ocean. Now, what do you mean by just right? So the Paleozoic has the just right concentration, not so low so that barite can precipitate, and not so high that the sulfate could be reduced to uh, H2S completely, which allow barite to accumulate in the sulfate-free water body. So let me go down here. So the Neoproterozoic seawater, this is the Paleozoic, right? So when you go back to Neoproterozoic, because we don't see any significant better barite deposits. Therefore, in the Neoproterozoic, all the way back, the seawater sulfate concentration must be lower than this Paleozoic just right. So they have to be lower in the overall sulfate concentration. But now, so the story, I'm going to go to the second story. That is looking back to the Ediacaran. So the seawater concentration must be lower than Paleozoic, even we know Paleozoic is not that high, and therefore the Ediacaran must have highly heterogeneous and both temporally and spatially in terms of sulfate concentration. So I'm going to look at two periods, two time window. One is at the very beginning of the Ediacaran, the base of Ediacaran. And the second is this Shuram event, or Shuram carbon isotope excursion event. So one is earlier, one is later. Okay, now the second story. Maybe I'm going a little bit faster, but we'll have time to discuss all this. So this is the three isotope parameter, kept delta 17, delta 18, delta 34 of sulfate from the basal Ediacaran barite. We know this very strange, or you can say interesting, occurrence of this barite crystal fan everywhere. Well, almost all the paleo continent that we look at, that you have this barite occur in the cap carbonate, somewhere not right in the bottom, but somewhere a little above the boundary between the dimictite and the cap carbonate, and you have this barite deposits, and they look very different from any type of barite deposits throughout Earth history. And here's the symbol. Here's the diagram I got of Paul's website, and all the fan-like places where we find the crystal fan of this Marinoan age, 635 million years ago. And also we know that they have this very distinct 17 anomaly, the mass anomalous 17 depletion in the sulfate, which is totally different from the aerosol sulfate, which normally has positive 17 enrichment, or got kept at the 17 positive value. Now, for this formation of this crystal fan, the barite fan, there are different models proposed by different authors. Grant studied this Northwest Africa basin, and he said, well, the barite must come from deep, and then met the shallow sulfur-rich seawater. And Paul 2011 say, well, yes, the bearing comes from deep and up well to the surface oxidizing zone. They kind of are very careful. I'm amazed that they're very careful. They didn't really say where the sulfate come from. And our group, Joe and Penn, we're more how do you call them? We're more brave, or we just say, well, because we know the sulfate has this native 17 anomaly or depletion, it must have this oxygen O2 signal gets into the sulfate. So the way we know is the pyrite oxidation. So we thought it must come from the river then. Although, yeah, because in order to form barite, you must have this barium and sulfate initially get separated. So barium, we agree, come from the deep, up well, the deep water. But sulfate, we thought it must come from river. Okay, now we need that because we call this river model of the source of the sulfate for this barite. We need that because look at this diagram. This is the supposed to be a paleo lake in this Svalbard uh, carbonates. You will see this very depleted or very negative capital 17 value. And in this, if you look at the right hand side, the sulfate an x-axis and the capital 17 in the vertical axis, you will see that they line up really well in a straight line. Of course, we think that, wow, this sulfate in this carbonate that we extracted, it could be a mixture of two M member. One is the weather, the one gets flooded into this lake. The other one is probably pre-existing sulfate that's in the lake, probably gets recycled many times by bacteria. So the capped out the value gets erased or diluted to become the water signal. So when you have this nice straight line, you would wonder what would be the end member value of that river sulfate. Well, if you extend this line, we know that the delta S34 of the overall river, if you add them together, probably very close to 1 or 2 or 0 even. If it's a 0, then the cap delta would be like -4 for sulfate. In -4, sulfur has 4 oxygen, probably only 1 comes from the air, and then you plus some dilution, you might have air oxygen like -30 per mil. So that was the reason that we need to know the M member, or why this is important to know the source of the sulfate. Otherwise, you will have a very different estimate of the atmospheric oxygen capped at the 17 value, which is important to derive to infer the CO2 concentration and the primary productivity. So that's the reason that we need to know that. And this is the oxygen side of the story, which the left side, the oxygen is also, it's not as good as the sulfate. They don't have a good line. And that's the red flag in the beginning. We know that something's not perfectly lined up. Now, that was the lovely LSU camps when I was there. Very close to Mississippi River. So we started this 4-year-long campaign. We sample one sample per week, sometimes per 2 week or half month for 4 years, exactly same time. It started 2008. Yeah, this diagram looks very busy, but it's basically from January or July 2008 all the way to July 2013. And you will see that the average, it varies a lot because we went through this dry period and the flooding period, but the average Mississippi River, the sulfate delta S34 is -2.7, delta 18 is 3.4. So we knew that if that's the case, then we should see some of the barite at least have this kind of value. But we don't see it. We always see them very positive, as you can see before, and very positive. This is the Shuram Lake, so there's excuse for that. So now until today, so this is the synthesis of all the barite from this Marinoan, from this cap carbonate, from at least the 6 paleocontinent, and you will see that. Well, this is the vertical is capped delta 17 of the sulfate, and the horizontal is delta 18. The delta 18, the most negative one, the one that's supposed to have very little, the least, mixing from other source of sulfate, in fact, had a very high value, around 17 per mil. The very negative one have a 17 per mil. I thought that, the very negative one, if it comes from river, at least you should like Mississippi, the 3.4. No. And let's look at the sulfur. So this is kept down to 17, and the horizontal line is the sulfur as 34, and the sulfur, the lowest one is plus 20. None of them lower than 17. But Mississippi, we know it's minus 2.7. And if you look at the pattern, they kind of converge to the same place. Sometimes you don't have the data, but they all, if you put all together, they seem to converge to that place. So what's wrong? It has been like the elephant in the room in our group. We know something's not right. Well, so just I think last year I started to compile, just look into those river sulfate data that had both delta O18 value and a delta S34 for river sulfate. But the river has to flow into the ocean. Now I pick a site that not close to the ocean because you're gonna be contaminated by ocean sulfate. So that's the compilation. As you can see, there's a large range for delta 34 and delta 18. And for example, from minus 2.7 to 10.4 for 34, and from minus 5, which is understandable, like I think it's the Mackenzie River or something, there, and to 10.5 in the French Alps where you have lots of limestone. So different river from different area of the world, when they have a sulfate flowing to the ocean, they have a large range of both delta S34 and the delta 18 value. And in the meantime, they have a relatively low delta S34 and the delta 18, the average value. And you can say that, or maybe the Marinoan has a very different continental or the configuration. Not really, they are very similar. You range from high latitude to equatorial area. And here, the same thing. These are barite occurrence, this brown fan-like thing. And they have a large range of different in latitude. So the river model has three problems. One is the delta 18 value of that barite is just too high. I mean, I'm not talking about 3 or 4 point high. It's more than 14 point high, too high compared to the average. And the delta 34 is the same thing. It's about 17 or 18 point higher than the average of the modern one. And also the third one is the range of either delta 18 and the delta 34 does not match. They're too narrow for the barite in the base of the acron, too narrow. So new model. I think we have to abandon that most of the sulfate comes from river. No, most of the sulfate has to come from different source. Where? We think it has to come from this wedge of seawater or water body on the shelf where the sulfate or pre-existing sulfate has been reduced completely to H2S. And in this sulfide rich, sulfate free, there's no sulfate. They get completely reduced because you need the help of organic matter. And then in this body of water, you will have a bearing that peacefully coexisting with H2S. And when they get up well to the shallow level, when they met O2, they will form sulfate, then will be immediately titrated or scavenged by bearing. So then you can form this red dots. These are the barite. If they flow or winnowing around and in a shallow place, they will form this barite fan. If they end up falling into the deeper part, they will be redissolved. So that's our H2S model. Now, I think this model can explain a lot of things. And well, I couldn't find modern analog. As you know, but because the modern seawater has too many sulfate, 28 millimole or 2,800 ppm. That's too many sulfate in it. But still, look at this is the coast of Peru. People sometimes smell sulfur because the upper weld one has a hydrogen sulfide coming up, gets oxidized, and these milky place, these are the elemental sulfur. And you will see the same phenomena in off the coast of Namibia. This is from satellite image. Those milky one, it will come up too. But the problem is that these are not good analog of what happened in the spatial ediacaran, because this one, even those H2S gets oxidized today, and they turn to elemental sulfur. Finally, probably become sulfate. But you have this huge crowd of already really concentrated sulfate in the seawater. So these newly formed sulfate added to the seawater probably don't see much signal. So that's what but in the Neoproterozoic or in the basal ediacaran, it's different because that's the only sulfate you get. So the signal, this kind of signal, is probably the best candidate to record the oxygen that dissolved in the seawater. So now there are a couple of predictions of this H2S model we can do. We can test later, but let me just list them. The first one is that the sulfate generated through the oxidation of H2S has to be characterized by a delta weighting value that's approximately 17 per mil more positive. Sorry, there's a typo than that ambient water. And now this is viable because we do have an experiment reported for H2S oxidation that forms sulfate. But unfortunately, that data, that report, that I think there are two studies there, they all emphasize that these are abiotic oxidation, not biotic oxidation, because we all, in the literature, the consensus is that if it's a biotic oxidation, biologically mediated oxidation, all oxygen in the product sulfate is going to come from water, not from O2. But this hypothesis need this sulfate to have O2 signal. Otherwise, you cannot explain this negative 17 anomaly of these barite fin. So that's one thing that has to be pursued in order to validate this H2S model. And the second prediction is this. So there has to be, I mentioned already a little bit, that at that time, sulfate has to be low enough that it can be completely reduced to H2S, where in that water body, barium and H2S can coexist. Now, there are few modern analog, but entirely possible in the ediacaran. Third, dissolved O2 at chemocline, where the H2S gets upwelled and met O2, that dissolved O2 has to be anomalous, has to come from the atmosphere, and then was incorporated into this product SO4. This is also viable, but as I said, there's no experimental study demonstrate that that's being the case. So this is the work that need to be done. Fourth, now since we say there's a body of water probably globally distributed, and in that case, the barium isotope of those barite fins should be relatively uniform, at least regionally, because the barium came from the deeper water, the sulfate-free deeper water. At this point, I think Pete Crawford work on barium isotope is consistent with this prediction. So So this basal ediacaran story basically tells that there is this very dynamic and up and down sulfate. Then sulfate gets used up in entirely pure H2S body of water, no sulfate at all. This kind of a phenomena is probably widespread and both heterogeneous in both space and time. So in that kind of condition, you would imagine, or I would imagine, that sulfur oxidizing prokaryotes is going to be crazily active in that world in ediacaran. Because the H2S will be oxidized, but then the sulfate can be completely reduced. Then on some cases, you don't have much H2S because they all got oxidized, or you have a lot. So it's a highly heterogeneous and dynamic. That probably would is kind of speculation. That probably going to be a good opportunity for sulfur oxidizing bacteria to survive, or maybe just start a new lineage. Now, and then I think this Canfield and Teskey probably will be happy about this. I think they had this wonderful paper back in 1996, and they used some of the symbiotic gamma proteobacteria that live in some of the bivalve to do the molecular clock work, and they found that this gamma proteobacteria subdividing this sulfur oxidizing bacteria is probably originated sometime in the Neoproterozoic. Maybe it's very tempting to speculate that this such a late emergence of the sulfur oxidizing sulfide oxidizing bacteria is related to this occurrence of H2S rich water body in the shallow ocean in the Neoproterozoic. Because back earlier, you probably don't have much sulfate to have this larger scale H2S rich water body. And later, getting to the Paleozoic or even younger, you don't have that too because too much sulfate around. Oh, the early time you have iron, sorry, yeah, iron's another player. Any time you have H2S, iron's gonna, scavenge that and form, eventually form pyrite. So taking away this possibility of a large body of H2S rich water. So this paper will be out soon in this National Science Review, this journal. We wrote it as a perspective because indeed there are a lot of new questions has to be answered before we can say, well, this H2S model has been tested, well tested. There are speculation in it, therefore it's a short perspective type of paper. Okay, now the third story, the Shuram carbon excursion. So as the seawater sulfate concentration increased, the basal ediacaran, we know you can have a sulfate-free water. And for the first story, I also indicate that the Paleozoic at least have a more sulfate in the seawater than the ediacaran. So this Shuram is somewhere between the basal ediacaran and the Paleozoic. So I assume seawater concentration has been steadily increased. I know steadily may not be monotonic. Maybe there's a jump, but so you will have a situation where when you might not be able to have this barite fan deposits anymore. The reason is that you no longer have this sulfate-free H2S water. So as long as you have a sulfate and the H2S, they can coexist like in the Black Sea and today. But barium cannot exist there if you have sulfate in it. So that that situation would, if you have sulfate that's left over in H2S body water, then you're unlikely to have a barite. So I think when you're getting to the later part of the ediacaran, that's probably be the case. So let's look at this Shuram. So this paper was by Wang Haiyang and Li Chaoyongbo, and we did this a couple of years ago. And initially, when we discovered this, I thought, man, this is the one of the probably the most exciting thing since our discovery in 2008 of this negative sulfate oxygen 17 anomaly. Then it turns out the story can be complicated, but in the beginning, let me say something. When Wang Haiyang came to our lab at the LSU, he said, well, I want to do CAS, the carbonate associated sulfate, for this ediacaran, this largest negative excursion, the carbon isotope excursion in Earth's history. Then we say, because we are so fixated on this barite thing, and we say there's no way you can preserve any 17 anomaly in those carbonate associated sulfate, because these are seawater sulfate. Seawater sulfate, they can be easily reset, by bacteria, because they're so low, bacteria using them a lot. And it turned out that Wang Haiyang didn't listen to us, which is good. Then he discovered something really, really amazing. So this is the South China, this Dos Santos Formation and Jolonwan section. I guess I could be wrong, and it's a large shift, probably 13 and 12 per mil native shift in the Shuram excursion. It's it's characteristic of many other places in the world during this time period. So then we went through this routine protocol that the Professor Pengbo developed. We got the 5-step dance. Basically, you brush them, wash with the sodium chloride water 4 times. Then you use hydrogen chloric acid to dissolve them. So every sample, you have at least 4 or 5 aliquot of the 4 water wash. Then the final one is acid, to make sure that at least the final acid one has little contamination from other sources. So we only report the final set, the one that extracted by acid, which we think it's more pristine. May not be pure entirely, that contamination free, but at least is close to the original sulfate in the seawater. So this is the sulfate, the delta S34. They have the same shape. But there is a little bit of delay, seems to, if you look at the carbon shift seems to be earlier than the sulfur shift in the CAS, carbonate associated sulfate, in those Shuram section. This is the delta O18 value of the sulfate. They also have the same shift. They also had a little bit of delay, slightly later than this. Then this one. Okay, hold on. Oh, sorry, go this way. Yeah. Then this cat delta 17 of the sulfate, carbonate associated sulfate from the Shuram. They also the same pattern. You have a native shift, then come back. Why is that? Well, that paper says a lot of things. I'm not going to go through this all, but let me show you that not only in South China, but also in South Australia and also in Tarim, Sichuan Formation, Tarim. Sichuan has slightly more the modern atmospheric contamination, but the general pattern is there. And this is the diagram showing this is kept at vertical is kept at 17, kept at 17. Just look at the solid field data, because the empty one is the water wash. There are, modern atmospheric contamination or pyrite oxidation, those kinds of contamination. You will see that the delta O18 value of the sulfate is much lower. Remember, that one is 17. Here it gets to the 8, only 8 per mil, indicating that it seems that the seawater already has some sulfate in them already, and or the H2S that's upper weld is not the sulfur, is the oxidation, it probably will be, maybe diluted by existing sulfate in the seawater. And for sulfur, S34, delta S34, is still quite positive. It might mean that the H2S or something that come from the deep still quite positive. The point is that if you look at all the data, the only reasonable interpretation is that during Shuram event, this native carbon isotope excursion, that there is accompanied sulfate flux that's greatly enhanced. In basically, the seawater sulfate see a large increase in concentration. And also the other thing that we conclude that the added sulfate, this extra sulfate added to the seawater during the Shuram, appear to have the same origin worldwide. And it was overwhelmed in quantity by this new one, because it's a sulfur and oxygen isotope composition are convergent to the same set of value across 3 different continental shelves, Taiwan, South China, and South Australia. They seem to converging to the same thing, which means that there's also a deep H2S reservoir in this Shuram ocean that gets oxidized. And that's the extra sulfate added to the system. Now, here's a question. So we think, well, if you think, going back to the old argument, then it can be either the pyrite weathering on land, or even some old evaporite, gets dissolved and gets into the Shuram, as some suggested. But also there's another possibility is in the deep ocean, the water column ventilation, just like the basal ediacaran, the barite fan, you can have a H2S, deep H2S ocean gets oxidized. So the modeling exercise show us that we needed to oxidize extra H2S in order to explain those data. And also, furthermore, the modeling research results show that it has to occur initially as a pause of oxidation, but that pause probably lasts a duration of 1.5 million years. So my point is that there's probably a continuous, intense, repeated oxidation of the old existing H2S pool in the deeper part of the ocean. So you have to have an oxygen, not oxygen, sorry, the water column ventilation in order to explain this shift, in order to explain this correlation between carbon isotope, the delta S34, delta O18, cap delta 17 of the carbonate associated sulfate. So that's basically the paper, the story of that paper. Now, this is my thought that beyond that paper, note that we're very careful in the title. We say that it's confirming the oceanic oxygenation and or water column ventilation or increase oxidation of pre-existing hydrogen sulfide. But two mutually non-exclusive processes can make that happen. One is, a lot of people wanted to go that way, that we have increased atmospheric PO2 during the Shuram. Yeah, if you have increased PO2, they're probably going to push the O2 deeper into these hydrogen sulfide water body in the deeper part of the shelf. But in the meantime, you can also achieve that by reducing organic carbon influx into the water column. For example, when you do that, you increase the consumption of O2 in the shallow part. Then called the ventilation. So you don't have lots of organic matter gets into the deeper part of the water. So both processes can help explain the thing. So for my own preference, I think it may need some quantitative constraint, but since there is native shift in the sulfate cap delta 17 during the Shuram excursion, I think it favors the second one. The reason is that we know that if the O2 concentration doesn't really change, but if you reduce the primary productivity, you reduce the organic influx, you will prolong the lifetime of atmospheric O2, which will help accumulate its 17 depleted signal. So, but this is something that we need to look at more data on different continents in the future. But I'll just throw it out there that I have my own preference exactly what happened. It may not be that atmospheric atmospheric PO2 oxygen concentration increased during the Shuram. Well, the second thought on this thing is that we just look at the Shuram, the excursion, but there are many other repeated excursions in the entire Neoproterozoic. That's what the title of my talk for. It's the Neoproterozoic thing. So there are a lot of new things we can do. We can use the same method and to look into the sulfate in those carbonates. So some of the highlights. Story one is that the temporal pattern of the bedded barite deposits show that even the Paleozoic seawater sulfate is low, but at least it was higher than the Ediacaran. And story two basically tells the story that the occurrence of a sulfide-rich and sulfate-free water body in shallow ocean of the base of Ediacaran is common. It's not strange, and it's an inevitable episode in the long history of the Earth's redox titration. Story three, the Shuram excursion is an ocean oxygenation event, but I'm not sure if the atmospheric PO2 increased. The many native carbon isotope shift event in the Neoproterozoic may have similarly associated the sulfate story as well. Stay tuned. So I'll thank all my co-authors for this work and also financial support from Nanjing University and the National Science Foundation of China. And thank you.
Great. Thanks, Huiming. We're going to switch to a question and discussion session. You can ask a couple ways. You can raise your hand or you can type your question into the chat and I'll read it for you. The first hand up was Greg. Please go ahead.
That was wonderful, Huiming, and very thought-provoking. I have two questions. Let me start with my first one. How do we know sulfur was so low in the Precambrian ocean? Because the paleosols are not at all low in sulfates. In fact, they're loaded with barite. How could the paleosols have so much and the ocean have so little? And what is the actual evidence for a low sulfate ocean?
Well, the earlier evidence is basically based on the salt delta S34 value of the pyrite. And right now I'm focused on the, my talks are focused on the ediacaran and the first evidence, even the Paleozoic, you don't have a better barite deposits. That's one of the evidence. The ediacaran must be very low.
Right. Okay.
Yeah.
But I'm intrigued by your Shuram suggestion, which is I noticed on your map of the world, the greatest sulfur fluxes and the greatest sulfur differentiation were coming out of high latitudes, out of cold climates, as opposed to, say, yeah, a long way back. But anyway, my point is the Shuram excursion, that's the one. Yeah. The Shuram excursion actually coincides with the Bu Azer glaciation in Morocco and tremendous paleokarst development that Nick Christie-Blick has now confirmed in South Australia, and I've looked at it as well. This was a time of low sea level, cold climate. Could that be the explanation for so much sulfate being introduced during that event? Or could the CAS sulfur signal be a signal of paleokarst or meteoric weathering of all that exposed limestone, which has been proposed for the carbon and oxygen side of the story as well?
Oh, yeah. Well, I don't think, globally, the sulfate flux from river would change much between cold climate and warm climate. I think it probably has, my understanding, it probably has more to do with the rainfall. Because we noticed that in the drought season and the flood season, the concentration of the river sulfate doesn't really change much. So like Kate Mayer in Stanford, they had this idea that because it's a transport limited process. So I don't think that there's a huge difference between cold and warm climate in terms of
it's more between rainy and dry.
Yeah.
But we have evidence in South Australia that sea level was lower by 600 meters during this.
Gaskia assuring?
This is Nick Christie-Blick has done this, and Chris van der Borch did it years ago, and I was there also. I have a paper on it as well. 600 meters lowered sea level. There's a lot more weathering going on that could explain your big sulfur flux, I think.
So
yeah, but that
is it global?
All has to be local. Can't be global.
Yeah.
I think it's global, but
Snowball Earth maybe.
Most of these submarine canyons.
Hi.
Yeah. Hi, Frank. Francis, do you have anything to add? No?
Yeah, these are submarine canyons. You can't show this as 600 meters of fall. Christie-Blick's made these arguments in the Western U.S. as well, and they're filled by deep water deposits. So until you can show that these are not submarine canyons, I don't think we can say there's 600 meters of sea level fall.
Interesting. Well, I looked at it and Chris looked at it, and we thought they were paleo canyons. Where is it in the United States, the Shuram? It's in the Johnny. Nick looked at that one too with Sarah Giles, and he thought that was a paleo valley as well.
Can we move on to some of this isotope data? So, I mean, I think you had some really interesting model here for the barites Huiming, and I was curious what the implications were for the preservation of the O17 anomaly.
Let me go back to that one. Okay. That's the third story, right? Yeah, this one.
Well, as a second story, as I was thinking about, is just for the barite,
second story.
You didn't bring it back around to what the implications were for the 017 anomaly, the large one in the caps. If you're producing this anomaly with producing the barites in potentially deeper water with H2S, how should we think about the preservation of the 017 signal, which is forming in the atmosphere?
Okay, the story like this, okay? Initially, we thought that O2 oxidized pyrite on the land, then washed by the river, and
Exactly.
buried, stay there, and trap them. And no, now we changed our story. We didn't say there's nothing come from river. They probably some come from river, but not significant. It is H2S. The body of water down there in the shelf that's rich in H2S, and no sulfate. Therefore, you have a coexisting bearing, and H2S gets upward to the shallow level where you have the redox cline, and on that boundary, it gets oxidized. And those crazy sulfur oxidizing bacteria probably played a role. But once they oxidize, that sulfate will immediately combine with the barium. So you'll see that the milky barite floating around. If they end up in a shallower, higher topographical high, which is more oxidizing condition, they will be preserved. But if they falling into reduced, deeper part, they will be dissolved. That's what we see in the field. You only see those barite fan in the high place, not in a low organic rich place. So that's the story how they gets preserved.
So you still think that the 017 will not be diluted, I guess, is the concern, is trying to preserve that 017 signal, that's an atmospheric signal when you have such a large seawater sulfur reservoir.
Thank you for bringing up that. Now, if there are existing sulfur in the seawater, then this newly formed barite, the barium will combine with other sulfate as well. But in those cases where it's a H2S plus barium kind of water, they will form, that signal would be very close to the initial sulfate that's formed by the oxidation of sulfide.
Yep.
So if you want to see a sulfate that has the most O2 signal without any other dilution, that's where you're going to see them. So now we have to revise all previous, if that's the correct model, then we have to revise our previous thinking, what the atmospheric O2's capital 17 value should be, maybe lower, not that negative. And maybe initially we thought probably like 30 per mil. Now probably we should think it as 10 or 15. So this also gives us opportunity, because we were thinking in this bearing H2S water body, you probably also have silica, you probably also have phosphate. And sometimes phosphate can trap those barite as well. So that's another thing we're looking into right now. So only those barite probably has the best or the most enriched atmospheric O2 signal.
Thank you.
All right, thanks. Next is Jingjun Liu.
Hey, Huiming, that was wonderful to see your talk. As a modeler, it's always good to get some new data. I have two comments, one on the hydrogen sulfur model, another on the organic carbon burial. I think when we look at the other data out there, the evaporite data, 018 in the Neoproterozoic, it can reach about like 30 per mil, like 018. And in the cryogenia, we have carbonate associated sulfate reaching almost like 35 per mil. So I think that's—
You're talking about delta S34 or delta 018?
No, I'm talking about 018. I think the strength of your hydrogen sulfur model is that if it's reacting with oxygen has about 23.5 per mil in 018. So that could explain the enrichment. But at the lower O2 in the Neoproterozoic, when you have 30 per mil, 35 per mil in O18, this is simply, well, certainly something else is going on. I would suggest that probably some CO2 signal in the carbonate, because right now they're 44 per mil in O18, and they probably become higher at a higher CO2. But I think the real issue is that when you involve a water body, right, evaporite from differently than barite. And the real issues in the Neoproterozoic I think is it is significantly out of equilibrium with the seawater O18, which is right now it's about 9 per mil, right? And I think really we as a community should address that. My second comment is on your Shuram explanation on the organic carbon. I think as a modeler, my opinion is that it's probably due to the late rise of land plant more than anything else. This is because the turnover time of atmospheric oxygen, as controlled by the growth or net primary productivity, is very quick at lower O2, about 10 or 100 years. Whereas the oxidation, the PO2 control through organic carbon burial is in the Neoproterozoic and still in the time scale of 10,000 or 100,000 years. So for if there's an equilibrium of the dissolved oxygen in the ocean and the atmospheric oxygen, if that's the cases, the dissolved organic carbon in the ocean shall have very limited role. And the reason I think personally that the land plant play a big role is a lot of the O18 signature in the present day oxygen is actually controlled by the Dole effect and largely controlled by the land plant. And Michael Bender has modeled the so-called Dole effect in the ocean, but one could argue there's a significant differences on the mass dependent fractionation O18 on the land versus the microbial or algae community in the ocean. Yeah, but just my comments. Thanks again.
For the first one, you mentioned the delta O18 of the sulfur reaches 30 per mil.
Yeah, that was from Peter. That's from Peter Crawford review paper. I think you are a co-author. I'm putting from my memory.
Really? Okay.
That is a chemical geology paper in 2019.
I'm pretty sure you. Yeah, I don't believe any data that any sulfate oxygen delta O18 data if it's beyond 25. That's questionable.
Well, yeah, but it's been reported. But the sulfur, the sulfur 34 data,
except when the water is like +8. Okay. That story about CO2, I know that story. I if you come to Nanjing or sit down talk, I'll tell you, I don't believe that. The second one about the land, we don't really know. It's easier to know. It's actually easier to know the cap delta 17 of O2 in the past, but it's much more difficult to know the delta O18 value of the atmospheric O2 in the past, because you see, well, 23 per mil of modern O2, but we don't know when they combine with H2S or sulfide SO3. There's a kinetic fractionation. We don't know what's in the number. It's a native one going up. So there are a lot of steps there. The cap delta, it doesn't really matter what kind of fractionation you have. You don't dilute them. That's it. So they don't change. So the Dole effect is a harder problem. If you look at Cao Xiaobing and there's a paper in PNS, dynamical model of O2. We did the whole thing based on cap delta 17. We tried to avoid the delta O18 because delta O18 is a whole mess. It's hard to get. It's just harder to model them because we don't have a parameter.
Yeah, the only thing I want to add on to follow up is that your ediacaran data is not that different from the Progenian or Neoproterozoic O18 data. And I agree, it's hard to, as a modeler, I struggle to model this effect. Yeah, thank you.
All right, thanks, Jinjun. We have one in the chat from Anna Rose Waldeck. Thanks, Huiming. My question is, why would we expect that the H2S water column oxidation leads to much higher delta 18O fractionation than H2S oxidation in rivers?
Good question. Pyrite oxidation definitely won't give you that high number, but there are at least 2 laboratory experiments to show that when you do the H2S oxidation, the fractionation between delta O18 value of the sulfate formed and the delta O18 value of the water can reach 21 per mil. And as I said, wonderful, 21. That's exactly what I want. I only need 18, so you can do it. But in the paper, they emphasize that that can only happen when all the oxygens come from water, because it has to be abiotic, some biotic process. So there are gaps there. We don't know, but this is like because the pyrite oxidation couldn't do this, and some parties say that H2S can give you this high delta 18 value, but there's one piece of a puzzle is the cat delta 17 doesn't fit because we need the oxygen come from air. So that's, I hope, we have a poster working on the experiment H2S, try to adjust all the conditions to see what with the labeled water to see what the fraction of oxygen can end up in the sulfate formed by H2S oxidation, as well as the delta 18 value fractionation. So this is a working in progress, but that's a good question. That's a missing piece.
Yeah, thanks, Huiming. I guess just following up on that, I had been curious, about different, maybe like oxidation in a terrestrial river versus oxidation in the water column, if those processes might be like follow similar pathways or be fundamentally different in some way. I guess, I was thinking about the relationship between the water, maybe on the continents being a lower delta 18O composition versus seawater. It could also contribute, but fundamentally, like, is the process of oxidation very different depending on the environment? Thanks.
That's a good question. If all the pathways are the same between the H2S oxidation and the pyrite oxidation in the river, then the only difference is the water delta 18 value. And let's say there's lots of debate on what the Neoproterozoic delta 18 value of seawater should be. Let's say it's 0, and the continental average is, we say, -7 or something. You only have that's like 7 per mil difference, and it's 3/4 of the 7 per mil difference. So that still cannot explain that almost 17 per mil or 14 to 17 per mil positive shift for this basal ED anchor and barite. They're too positive. And I don't know, maybe you have a great idea, because it's an elephant in the room for our group for a long time. This is just too positive. And we always come up with excuse to explain it. But now I think we have to face it.
Thank you. Thanks. Next we have Daniel Segesman.
Huiming, that was a really fascinating talk. Really interesting to think about, the sulfate flux and how that has changed throughout the Neoproterozoic and into the Phanerozoic. And I was curious, Jingjun mentioned the advent of plants, but I was wondering if the mode of weathering on terrestrial surfaces and how that has changed through geologic time, particularly with the advent of plants. Do you think that could change the rate at which sulfate is being delivered from terrestrial surfaces to the oceans? Because there's been a lot of papers recently about how plants have really changed how terrestrial fluxes have worked.
Two points I can make. One is, as I mentioned, I like K. Mayer's group's work. Basically, it's a transport limited process. in my own experience, start from the Mississippi River, that I find that when the river discharge is only 1/3 of the flooding stage, but the concentration of sulfur is still the same. It's very strange. Then you look at the whole world ocean, 2, 3 magnitude the discharge change, but the concentration of sulfur doesn't change. So which means that the oxidation is not rate limiting step, it's the transport. So yeah, you have plant roots or Neoproterozoic. I don't think you have a plant roots, but some liking. I don't think they can make much difference. And the second is that, let's say the deeper roots can result in more iron-3 involved in the oxidation or the electron transfer from sulfur to sulfate, then you won't have oxygen signal gets into the sulfate. But what we observe in the ediacaran or Shuram, you still have an atmospheric O2 signal. The only thing, when you see negative anomaly, you have to conclude there's an O2 signal in it. There's no other way. So I don't think I'm not gonna be bet on some land plant in the Neoproterozoic to change all
Oh yeah,
this.
no, I wasn't insinuating. It was more that you stated that as we move in the Phanerozoic, we get more sulfate in the oceans, and that I know there's a recent paper that came out that was suggesting that when you do get plants in the Devonian, forest widespread, that organic acids from plants could actually have enhanced weathering from the continental surfaces, and that in the Neoproterozoic you have the absence of that more or less, and maybe that was what is slowing down transport from the continental surfaces, essentially.
Well, in terms of why the sulfate concentration increase in the Phanerozoic, well, I just blame oxygen. You have much more oxygen left behind, so I don't have to use sulfate anymore. Back in the Neoproterozoic, you don't have much oxygen. Sulfate is the most important electron acceptor. So it's like you're talking about drama, right? In the beginning, the 5 guys in the fighting. And who is the drama queen in the Neoproterozoic? It's the sulfur. After that, today, sulfur doesn't really matter. Oxygen is a drama queen. And way back, it's probably iron.
Interesting. And then, sorry, I know there's other questions, but to follow up with that, the enhanced sulfate flux that you're looking at during the Shuram, do you think that has anything to do with the increased orogenesis associated with the building of Gondwana?
Yeah, I don't, probably related. And some people also say, glacier. Yeah. But glacier and orogenesis happens all the time. And it should not be unique here. I've been talking to Professor Bing. I think that idea actually, I haven't dig deep into it. He mentioned that what is it? A canthomorphic aggregator? Those floating eukaryote floating creature totally died out. That would pretty much stop the transport of organic matter into the deeper part of the ocean. That actually would make a lot of sense for much of the data, but I haven't got a chance to dig deep into that. But then you can ask why they died out that time. They didn't show up until way later into the Cambrian. But then, yeah, I don't know why they died out. And he said maybe that's because of glacier. Who knows?
Yeah, that's interesting. Interesting to consider. Well, thank you. I appreciate it. Very interesting subject.
All right, thanks. Maybe we can go to Paul and then come back to Greg.
Yeah, I have 2 points or questions, both regarding plants. The first is that most continental weathering occurs in mountains and on alluvial plains, and in neither of those areas are plants particularly important. And my second question is that if Neoproterozoic sulfate was much lower, then am I correct in thinking that dimethyl sulfide, biological dimethyl sulfide production would have been less?
Yes.
And if that was true, then the oceans would have been much less cloudy, which would mean that the ice albedo feedback would be much stronger. And so you know where I'm headed with that.
Yeah. Yes. I don't have a intuition when the cloud nuclear condensation nuclei, when that small cloud is small, less covered, what would be the effect to the climate at that time in terms of many other things going on at that time. So you're suggesting, Paul, it's what will be more sensitive to the I don't know.
Yes. Yeah, if the oceans are very cloudy, then the ice albedo feedback is much weaker
Yeah.
because it doesn't make so much difference whether the ocean is covered with ice or not if there are a lot of clouds. But if there are fewer clouds, then the ice albedo feedback is stronger. And so models which allow the water belt state to exist, it turns out, are only models in which that have very strong marine clouds, which is true today, but may not have been true at times when the seawater sulfate was much lower.
Okay, so you're back to the snowball world now.
Well, yeah, of course, that makes
Okay.
it makes it easier to get into the snowball state if the ice albedo feedback is stronger.
Okay. Yeah, but you see, my three stories are always after snowball. And my title about Neoproterozoic is because I wanted people to realize that the tool we developed, looking into this cap delta 17, the native of the sulfate in each of those native shifts is going to change the whole thing. It's going to add so much to this dynamics of a Neoproterozoic, the world, that critical transition, it made you live in an interesting time. I want to live in the Neoproterozoic because it's a transition from this iron world into the sulfur world, and before getting into the oxygen world. So this sulfur is in this great dynamics there.
Yeah, I agree.
Mm-hmm.
All right, thanks, Paul. Greg, you wanted to revisit something? Or?
Yeah, I'm loving this conversation. This is really touching on some fantastic points. On the question of land plants, as Jinjung raised, they're obviously not plants. That's a taxon that didn't evolve then, but there were lichens, and several have been described recently. Lichens, you can't dismiss them as weathering agents because pot experiments show that they increase weathering by an order of magnitude. And then plants increase it in several orders of magnitude above that as well. This has actually become very clear from studies of paleosols now, which I've tabulated. There was a huge rise in the rate of weathering during the late Cryogenian to Ediacaran in terms of base elements like sodium, magnesium, potassium, and calcium. That's one data set that shows that a lot was going on land. Another data set, Ilya and I have compiled oxygen and carbon isotopes on petagenic carbonate and also paleocasts, and they also ramp up tremendously in the Cryogenian through Ediacaran. So biotic effects, I think, are pretty important to consider in this big transition that you're talking about. I'll send you those papers, and I'd be interested in what you think.
Sure.
Well, modern lichens only evolved in the Carboniferous, all the components of modern lichens. Now, there may have been lichen-like, symbioses that predated that, but they weren't modern lichens anyway.
Oh, you're right. They're not modern lichens. No, it's fairly clear now that the ones we have described are glomeromycotin not ascomycotin or basidiomycotin. Some of them are excluded from lichens by some modern lichenologists because they didn't have historical connection to their photosymbiont. They actually imprisoned them within a chamber, like a modern thing called geosiphon, which is found in forests in Germany. So yeah, they were different, but they were eukaryotic, large organisms with a great hunger for nutrients in soils.
Well, that's a hypothesis.
All right, let's go ahead. Andre, you had a question?
Yeah. So I wanted to ask about first part of your story, sort of about low sulfate and barium in the ocean. And it was a long time since I looked into it, but I think for barium and sulfate to coexist, you need on a scale of micromole of sulfate, a very low sulfate level. And so it seems like your model would predict that in upper part of the ocean, an oxygenated environment, you would sort of have mixing between sulfate and barium and precipitate barite. And so barite should be sort of widespread in shallow water environment until ocean was oxygenated and sulfate level would increase. And if you look on distribution of barite through time, like there are examples like 1.8, I guess you show them from India and other cases, also early Paleozoic in South China, but way typically associated with organic rich sediments, kind of anoxic sediments. So it's not really shallow water oxygenated environments. So they are more consistent with maybe methane seeps environments. So, and second point, there are sulfide evaporites in mid-Proterozoic and Neoproterozoic. So how do you reconcile this very low sulfate that you need to dissolve barium with somewhat higher sulfate to form sulfide evaporites?
Well, evaporite can be formed in a very local environment. So it may not be an open ocean, but barite, those better barite has to be in the open ocean. You needed the bearing to you have to accumulate lots of bearing. Yeah, reduced condition, you can have a bearing, but you'd better not have a sulfate in it. Otherwise, the bearing won't accumulate.
But with early Paleozoic barites, they associated with very organic rich shales, like with iron speciation showing like anoxic environments. So how?
Yeah, you're talking about this corner low right. Those are relatively the darker, but there are also places that's pretty. We see quite often massive better barite in the dolomstone section. It's actually more oxidized condition. And in fact, the Dr. Han, who is working on this area, I think he's probably online. If he can jump in, he's been looking at those sequences, and he found that if you wanted to find a good, thick, economically valuable barite deposit, you better to find those shallow dolostone sequence, not in those black shell ones. Black shell ones tend to be thinner.
But we all underlined by this very organic rich shales, like in early Paleozoic or in India. So you can potentially infer that that's environments where you generate methane with barium dissolved, and as it seep out and interacts with seawater, that's where you would precipitate barite.
Yeah, the problem with that methane source is that then it's hard to explain those lateral extended, like, tens of kilometers layered horizontal that cannot be from a seep. seep will be blocked. I would imagine seep would be just like chaotic thing, one big dome like thing right here that you couldn't have this layered one.
But you can also turn it around and say, okay, early Paleozoic, you can go in North America, and they don't have barites. So why is it restricted to South China?
I think you still also need the source of the bearing. South China is probably more hydrothermally active. And associated with the barite deposit, you have many other, zinc sulfide layer or copper sulfide layer and lead sulfide even. So there are a lot of, you have to have a source. I think a bearing probably, come from this, benefited from this hydrothermal activity.
Yeah, I totally agree with you. But when it's come to question, is it a global phenomenon or it's a local hydrothermal? But maybe we should talk about it later at some point.
Now we can talk more. I'm not sleepy anymore.
I was just thinking it's probably getting late over there. So maybe we should let you off the hook.
That's okay. It's okay. You guys have I'm asking this question. I think where is that? Oh, about Canfield, this one. Well, this words gets messed up. This is very strange. Why the gamma branch of this proteobacteria, where the sulfur oxidizing bacteria evolves so late? Don't you think that because of the H2S ocean only exist, those water only really exist significantly at that time in the late Neoproterozoic? Would that be part of the reason? I know this is not a causal relationship, but it's a good correlation in terms of timing.
But I'm not sure if it's paper from 1996. Is it still accepted with, like, it was based on sulfur isotope fractionation?
No, it's based on symbiosis. Some of the bivalve, they use the genetic molecular clock work.
Yeah, well, molecular clock you can probably turn anyway.
Okay.
You want, but one of the evidence was large fractionation that required sort of more than one step, sort of in sulfur processing. Okay. And I think now people see larger fractionation, certainly in Paleoproterozoic. So I'm not sure if it's widely accepted that sulfur oxidizing bacteria appeared, but I could be wrong. I'm not expert.
Yeah, but those ideas, those correlations are very, very interesting to think about, but it's harder to establish. Why they evolve at that time. Why can't they evolve? These are prokaryotes. Why can't they evolve earlier? Why the sulfur oxide and why it's so late?
Yeah. Well, Sichi Lee wanted to ask a question, so go ahead, Sichi.
Yeah. Could you hear me, Huiming?
Yes. Yes.
Okay, great. Okay, thanks for the talk. Very, very good. I have a more general question about the cycling of sulfur. So, especially for the riverine, I'm wondering, like, if there would be constraints on the proportions of the sulfur sources, the contributions of different sulfur sources, like the pyrite. Okay, the pyrite could be oxidized, but in the crust, the sulfur could achieve hundreds ppm, so relatively low, but the crust is kind of like the continental crust is always there. So I'm wondering, like, if there would you expect the different source contributions of the to the riverine sulfur along the geological history?
Well, I don't think of the sulfur in the crustal material is in the sulfate form.
No, it is not in the sulfate form, but
Yeah.
they like the reduced sulfur.
You mean it doesn't have to be pyrite. You can just weather basalt. You can also contribute sulfate into the. Oh yes, of course, yeah. Well, here's another maybe wrong conviction. I think that the atmospheric O2 probably already surpassed the threshold of the linear window where you increase the partial pressure of PO2, partial pressure of atmospheric O2, you would increase the weathering efficiency of sulfur to sulfate on the continent. I think that threshold has been passed once the atmosphere had 1% of today's O2 level. So any increase later, like let's say, any Neoproterozoic so-called increase of a second oxidation, you're not going to increase the flux of river sulfate into the ocean. So again, go back to that question. I don't think it's the source of oxidation or how big surface area or my root, the plant roots can increase the depth and the surface area. I think it's all the transportation. That's the limiting the amount of sulfate getting into the ocean. Once I asked one of the modeler in PK University, professor who I said, well, can you model last 200 million years the overall rainfall change on the continent? I say that might tell me the amount of the sulfate riverine input that should be correlated. I forgot. I think there are changes in the total rainfall. So I think the rainfall may be more important than the initial source, how you increase the surface area.
Okay, I see. Okay, thank you.
Or maybe a quick question. At the end of your talk, you considered, well, towards the end, two possibilities. It's increase in atmospheric oxygen versus decrease in organic carbon. But both wouldn't result. Let's this slide. So if you increase atmospheric oxygen level, it would increase residence time for oxygen. So why these two options have different predictions in your mind? Is it because
if you increase the PO2, you would resulting the oxygen penetrate deep into the H2S dome, the deep water. You result in further more oxidation of H2S, right? But in the same time, you can also achieve that by reducing the flux of organic matter into the deep ocean.
Mm-hmm.
Now, when you reduce that, which means that you reduce the primary productivity. If the Shuram is an event of a dramatic reduction of a primary productivity, then you are prolonging the pre-existing O2 in the atmosphere. You would result in the O2 accumulates a negative 17 signal. And then you can achieve both the native signal as well as the further oxidation of H2S, because you don't have oxygen is not used up by the falling organic matter because your primary productivity gets reduced. So I don't know what is the ultimate reason for both. It could be the die out of those eukaryotic acritac, the floating acritac. It could be a glaciation. I don't know.
Well, there is also meteorite.
How can we find out?
About what time? Ackermann impact, isn't it? About what time?
You mean impact?
Yeah.
The glacier
Australia.
glacier may not reduce the primary productivity. I think the extinction would reduce the primary productivity.
All
Okay.
right. Tao Han, did you want to chime in or ask a question?
Yeah, I want to explain our slice model of massive bodied barite for Android. So, our model suggests that both the bodied barite can be formed in the church or in some or overland some dolomite, because the barium ions can be accumulated in the anostic water, but the barite can be deposited directly in the same site, and also can be upwelling transported to the shallow water to form the barite deposit. This depends on the if at the anostic conditions, if the sulfate consume used if the sulfate reduction stopped, so the barite will be deposited at the under the anostic conditions. So that's why some bodied barite hosted in the church. So the barite, although the barium can be accumulated in the under the anostic conditions, so the barite deposition depends on the sulfate. Where is it? I don't know if I can explain the bodied barite sometimes hosted in the church, sometimes overlying in the dolomite. So I think it's depend on the sulfate near the this barium accumulation sulfate-free water. Huiming can explain something for me.
Well, if I answer Andrew's question, I just say, well, as long as you have sulfate, then you have a bearing. When wherever they met, I don't care. If they met some on top of a black shell, so be it. They're still gonna precipitate a barite. And even the top of a black shell doesn't mean it's an oxygen, right? So, and besides, if you have a sulfate, it can be oxygen free too. So it's okay as long as you have a large amount of bearing and a large amount of sulfate, they met together, then you can precipitate.
So I'm wondering if you compare, like in Black Sea, you have euxenic conditions, but it's still very sulfate in deeper part of Black Sea. Is this level of sulfate is it too high, I guess, for barium to coexist? Or
no, you cannot have bearing.
Yeah. So how do you?
It's not. You cannot. The tiny amount of a bearing, the bearing is insignificant. The story here, the key story here is that when we think about the ediacaran, we have to think about a water body that's H2S rich, bearing rich, but no sulfate at all. That's the key thing. At all means that below 10 to minus something. We don't have a modern analog of whatsoever like that. No, we don't have a modern analog of a water body like that today, anywhere in the world. Oh, maybe one place. Yeah, well, there's the one, Pierre Catherine. They went to this this island in Madagascar, northern of Madagascar. There's a little lake in the bottom. That's they find this. It's a water body. It's all H2S, no sulfate. That's the only exception.
Yeah, I'm just curious, is there some limit at which sulfate reducing bacteria cannot anymore reduce sulfate. So is it sulfate high in deep part of Black Sea because at that level sulfite reducing bacteria cannot reduce it, or is it high because it's still there is influx from global ocean?
I think it's just there are plenty of sulfate in the Black Sea seawater, and also you have so much oxygen there. Even H2S, gets upwelled into the shallow ocean. They all turn probably 100% back into sulfate. So it's the oxygen. Too much oxygen right now.
Yeah.
All right.
Okay.
Thanks, Huiming.
Hey,
I
thank
think
you, Alex.
we've been at it a long enough time, and this has been great. Really good discussion. So,
Thank you.
all right,
Nice to
everyone,
see you
take
guys.
care.
Nice to see you guys. Oh.
See you.